Yeah, I hope that you are able to see the screen now. So let us continue from here. So as I explained, right? So this is how the nested parallelism works, and we saw how we can use the nesting, right? So and we'll see more examples in today's applications. In today's application that we'll look. So yeah, let us begin from here, and do let me know if you want me to repeat anything. There is something in chat. Let me quickly check that. Okay. Yeah, let us continue from here now. Yeah, so we saw this runtime routines. Now let us quickly start with the matrix addition. So this is the first most simplest application that we want to look for today. So essentially we want to add two square matrices, and the way we perform addition for square matrices is highly simple, right? So what we want to do is that we have two square matrices A and B of size n cross n, and we want to add those two matrices, and the way we perform the addition will be quite simple here. So let me go back to my whiteboard. I think my whiteboard is okay. Let me check that. Yeah, my whiteboard is open. So let me pull this out as well. Yeah. So
Just if you don't mind, can you explain this alone once again?
yeah. So yeah, I'll explain this again. So
Thank you.
what I was trying to say in this example. So if you remember the example that we saw, right? Let me quickly go back there as well. So the example that we saw, right, in this nested parallelism, we have two parallel regions here, and one is nested. The second one is nested within the first one. And what we were asking ourselves is that how many times this cout will be executed, considering that nesting is true and considering that nesting is false. And what we saw here in the whiteboard, if you remember, is that when the nesting is enabled, that is nesting is true, what we saw is that this is how the execution will look like, right? There will be a master thread in the uh, serial region that will be executed as soon as it will hit this hash pragma will be parallel with number of threads as 2. So we have assumed here that thread count is 2 here. So it will it will generate two threads, team of two threads, and T0 and T1 will execute. And within this parallel region, there was a cout, right? If you remember. And so these two threads will execute the cout, and it will print two lines of outputs. And once this thing is hit, right, this nested parallel region is being hit, what each thread within the team will do is that it will spawn its own child threads, and it will be the master of its own thread team. So here T0 will create T1, T2, T1 will create T0, T1, T1 will create T0, T1, and the cout which is there in the nested parallel path will be executed by these four threads. So four times. So total 4 plus 2, which is 6 times it will be printed, right? That was what I was talking about. And considering that it is disabled, what we saw is that this cout will be printed 2 times, right? This one will be printed 2 times. But this nested parallel, this hash OpenMP parallel that is nested within the outermost parallel part, right? So this one will not execute since nesting is disabled. And what will happen is that this cout will be printed by just 2 threads, because these 2 threads, T0 and T1, will continue executing as they are. So this cout will be printed by 2 threads. So in total 2 plus 2, which is 4. If there are any questions, then please feel free to ask here. So this is what is nested parallelism, and it can be enabled and disabled by using this runtime routine.
Oh, okay, understood. Thank you.
Okay. Yeah, so let us move ahead since we have, I think, quite a lot to cover for today. I was talking about this. Okay, yeah, I was talking about this matrix addition part, right? So within matrix addition, what we saw is that we want to multiply two matrices A and B, right? And the way we perform addition is quite highly simple, right? So if you have this element A 0, 0, B 0, 0 here, so we'll add these two, right? In the resultant matrix, we'll do this A 0, 0 plus B 0, 0, right? And then A 1, 1, or sorry, A 0, 1, B 0, 1, and so on, right? Considering that this is 0, 1, 0, 1, right? So this is how we'll perform the addition element by element. So that is how we perform the matrix addition. Now, quickly coming back to the code, how will we code this up? That is what we want to look. So let us go back to the code screen here and let us see this matrix addition part. So initially we are declaring this m and I and j, variables. So m and n is nothing but the rows and columns in this matrix that we want to add for A and B both. So both of them are of same dimensions. And then we are having this loop variables I and j. Then we are declaring this A, B, C as the square matrix, not square matrix, but the matrices of size m cross n. And then we are taking the input for A and B. Then, yeah, we have set the nested parallelism as true here. And what we are doing is that we are then using this two nested loops. And within this loops, what we are doing is that we are adding these two matrices element by element, as you saw in the whiteboard, right? And we are placing the values one by one in this final matrix C. So this is highly simple, right? There is nothing cool going on here. So my question is simple here. First of all, considering that I have placed default as none here, what should be shared? What are the shared variables and what are the private variables here? That is the question one. Question two is that how many loops can we parallelize? So can we parallelize the outer for loop? Can we parallelize the inner for loop? That is what I want to know from you people. When I say I want to parallelize when I say we want to parallelize the loops, we are not concerned about the parallelization. We are concerned about the correctness. So we want to know whether there is any data race or loop carry dependencies. That is what we want to know when we parallelize, right? So considering that our code is race free, that should be our top priority. How many loops can we parallelize? That is question two. And question one is what should be shared in private quickly. Anyone?
There won't be any race condition, I think so. I don't know.
Okay.
The inner for loop can be parallelized.
Okay, so you are suggesting that this can be parallelized. Fine.
And then I and j can be private. And m and n should be shared.
Yeah,
Then,
this is absolutely correct. So M and N can be, M and N can be shared since those are the dimension for the matrices. And there is something more to it, right? We are not just using M and N. There are others as well, right?
So A, B, and C should also be shared.
Yeah, so A, B, and C should also be shared. And IJ should be private actually, because those are the loop variables and each loop should have it, each thread should have it as the private copy. Apart from that, yeah, the point is, would there be a data race here? Simple answer is no. I'll explain it why. Because let us assume that we have parallelized both the loops, right? So I'm considering the case with most complexity here, which is the case where both the loops are parallelized. Will there be a data race? Let us look into it. Let us quickly go back to the whiteboard. So the point that I'm trying to say here is that, yeah, let me pull a new page here. So what will happen when, let me go back instead this will be back. Yeah, so I hope you're able to see this screen now. So yeah, so what will happen when both the loops are parallelized? So outermost for loop is running over all the rows, right? Let us say this is row 1, row 2, row 3, and so on, right? Outermost loop is running over all the rows. Innermost loop, the second loop, which is inner loop, is running over all the columns, right? So essentially by parallelizing the outer for loop, what we are doing is that we are assigning the set of rows to a particular thread. Now, in worst case, what might happen is that each thread might get one particular row, right? Now, the way we are performing operation here is that we are adding element by element and we are not reading other elements while doing that operation. So this element and this element, so zeroth element of some A0, 0 is being added with B00. and so on for A11 or A10 with B10 and A01 with B01 and so on. Now, let us assume that you have parallelized both first and second for loop. In that case, what will happen? In worst case, what end up might happening is that so by parallelizing the rows, what you are doing is each thread is getting a unique, one single row in worst case. Each thread is working on one single row. And by parallelizing by parallelizing the second loop, what you can, in worst case think of is that each thread is working on one particular column. So in worst case, what might end up happening is that each thread is particularly working on one particular element. So if that is the case, let us assume that that is the case. You have parallelized both and each thread is working on separate row, separate column, and at the end it is working on one element. What will happen is that each thread will add this thing, that is, it will add A of ij plus B of ij. And this I and j are unique for each thread, right? Because the way we are performing the operation is this, right? I and j will be different for each thread. And it will place it in C of ij. Now, if you see it properly, there is no data arrays or any loop correct dependency here, because each thread is reading from these two arrays and writing it to a separate copy at this third array, third matrix, which is C. So I hope this is clear that there is no data arrays, because here the reading is happening and writing is happening in the separate matrix. So there is no data arrays here. So I hope this is clear. And even there is no loop carry dependency, because each thread is working on its own set of values, and loop carry dependencies are, those happens when we read some value and write it in that particular value at the same time. Here, reading and writing are not happening on the same values at the same time. So reading is happening from these two matrices, writing is happening here. So no data arrays, no loop carry dependencies. So considering this part is clear, what we can say here is that both of these loops, both of these loops are parallelizable. Considering that we have enabled the nesting, this is the valid thing to do. Syntactically as well as semantically. So this is not, this won't give incorrect results. Yeah, so I think that's it for matrix addition, I think, yeah. And yeah, I'll post this code so you can try it with few large values. So here I have just created some dummy, I'm inputting some dummy values, but yeah, you can in general try it for large values, running it for large matrices, actually, large matrices, and see what's the performance, for the serial and the parallel part. Also, one more thing that you can try here as homework is that you can try different form of scheduling here that we learned, right? If you remember, we learned three types of scheduling. One is static, dynamic, and guided. So you can try and see which one is giving better performance in this case, right? So that you can try. Yeah, so that's it. Now let us look into the second one, which is matrix multiplication, right? So let me share my slides quickly. So matrix multiplication is again quite simple according to me. So what will happen in matrix multiplication is that we are trying to multiply two matrices, and the condition here is that the number of number of columns in the first one should match with the number of rows in the second one. And the in typical way, the way we perform matrix addition, multiplication is like this. Let me share my whiteboard. So the way we perform the multiplication for matrices is like this, right? We have two matrices here, A and B.
I think here only the inner loop can be parallelized, right? Not the outer loop.
We'll see. We'll see that.
Okay.
We'll see with the proper understanding, like what can be parallelized, what cannot be parallelized. And in fact, I'll ask you people also to think here. So the way we perform the multiplication is highly simple, right? If you people know, we take this column, we take this row, we multiply each of them element by element. So let us say that this is A00, A1, sorry, A01, A02, B00, this is B, B00, B010, B, 2 0, right? And we want to fill this C0 0. So how we do it? That's highly simple. Like this, right? We do this like this. Do it like this. So yeah, this is how we fill this one entry. So in general, if I generalize this equation, what we did for this, right? By multiplying this one and filling this element. What will we do is that Cij is equals to Ik into P of Kj, right? This is what we do for matrix multiplication. So yeah, this how, okay, let me write it in one more detailed step. So this is nothing but I0 into P of 0j plus A of I1 into P of 1j and so on, right? This is what we are doing here. And if I generalize it, it is like, in short notation, it is like this. So this is the main thing that we are doing here. Now, coming to code quickly, this is also a very simple application, but from a parallelization point, it is quite important to understand how to parallelize it. So hence I've picked this up. So yeah, let us pick this up as well. Sorry. Yeah. So here again, this is the code for matrix multiplication. What we are doing is that we are defining three matrices A, B, and mult. Mult will be the one which will hold the final answer. And then we have this rows and columns for the first matrix, rows and columns for second, and then I, J, and K for the loops. These are looping variables. Then we are taking rows and columns as input for both of the matrices. Then we are checking this thing, right? The column in the first one should match with the row in this row in the second one, in the second matrix. And if that is not matching, then we'll stop here. Else we'll take the input for both the matrices. You can play around with the matrix size and the input size as you want. But the point here is that the parallelization part, right? So we have set the nesting as true. And here comes the interesting part. We are initializing the final matrix where we are storing the answer as all element within it are initialized to 0. And then we are performing the multiplication. The way we are performing the multiplication is simple, as I explained. What we'll do is that we'll go over all the elements in the final matrix. So if you remember the final matrix, let me go back here. So let me pull this out. Yeah, so this one has the dimension R1 into C1. This one has R2 into C2. So the final one will have the dimension of R1 into C2, right? So what we are essentially doing is that we are looping over all the rows of this, all the columns over this. If I go back to the code, we are looping over R1, looping over C2. That is, we are looping, we are going through each and every value in the final matrix, which is mult. And what we are doing is we are trying to fill that value. And the way we'll fill that value is based on the formula that we saw, right? So this one is what we saw here. Yeah, so this is what we saw, right? This is one, the formula. So, okay, let me go back. Yeah, so this is how we'll fill the values. Now, the question is simple again. What all can we parallelize here? Can we parallelize the outermost loop, the second loop, or third loop? How many loops basically can we parallelize here? Please think about it. And when I say we are able to parallelize, what I'm trying to say is that we should be able to parallelize it without any data race or loop current dependencies. So I think for this loop, we can parallelize both, right? Because this is very similar to matrix addition part. In matrix addition, we were performing addition. Here we are just initializing it. So that's the difference. And for that case, both loops were parallelizable. So here also both can be parallelized. The tricky part is this one where we are performing the multiplication. What I want to know from you people is that how many loops can we parallelize here? maybe I'll wait here for a minute or so, and maybe then we can discuss what can be the
But
possible
there will be a race condition, right? For
for which
for every time when we multiply a, b, and then add it to the existing value, there may be a race condition.
okay,
If we
so
parallelize everything, I mean outer loop, outer and inner.
okay, so you are trying to say that there can be a race condition, but okay, if there is a race condition, then what would you recommend? Or okay, first tell me one thing: how many loops can we parallelize, avoiding the data race?
I think the two inner loops, j and k.
Okay, so you are recommending this thing. Is this correct? Anyone would like to comment?
So I think parallelizing innermost loop will lead to data race. We may parallelize the outermost loop, but not the innermost loop. And
Okay.
for second loop, I am not sure.
Okay. Any other thoughts? This is good that you people are giving your suggestions, because that's the way we'll be able to maximize our understanding. But yeah, let me know what you people think. What can be parallelized here?
So we cannot parallelize the innermost loop because mult ij is going to be accessed by each iteration, and that would actually result in a data race across all iterations. So except for the innermost loop, we should be able to parallelize everything else. So I and j should be parallelizable, but not the k loop.
Okay. Multiple suggestions here. One was we can't parallelize the outermost. I think Mitesh suggested that we can't parallelize the innermost. Someone said that, yeah, I think said that we can't parallelize, or we are not sure about the second group. Okay, so let me add my thoughts here. What I think about parallelizing. So, okay, let me share my whiteboard again so that we can understand it better. Okay, tell me one thing, right? What are two outermost loops doing, right? As I told you, the two outermost loops that we have, they are doing nothing but they're going through each element and doing this operation, right? So if you think about this, right, this problem, two outermost loop are doing nothing but they're going to each element of mult. Mult was our third array, right? Third matrix, right? Each element of mult and doing this operation. So basically taking this row, taking this column and placing value here. Now, do you see any data race here happening? If this is the case, let us pick up for this example, right? So for first row and first column, it is multiplying in this manner and placing the value here. Do you think that there can be any other thread, considering that each thread is working on a single cell of this matrix? So let's say there is one thread for this cell, one thread for this cell, one thread for this cell, one thread for this cell. This will happen when you have parallelized both first and second outer loops, right? So this will happen when you parallelize this outermost two loops. Now, considering this, right, each thread is working on each cell in the worst case, right? In the worst case. So in that case, what will happen is that these two matrices, this one and this one, are just being used for reading. So these two matrices are being used for reading, and you are reading them and doing some calculation and placing the values. And each thread is placing values in different cells. So if you think about it, there is no way a particular thread is writing to the same entry at the same time, or reading or writing to the same entry. I mean, one thread is reading and other is writing to the particular entry at the same time. So these two are being used for just reading. Each cell is being used for writing, and hence you can parallelize both of the outer loops without any race or loop carry dependencies. The interesting part comes when you even try parallelizing the third loop, which is this one. So let me go back. Yeah. So what we saw so far is that these two can be parallelized. So these one and this one. Now, the interesting thing comes when you parallelize the third one as well. Now, when you parallelize the third one, what will happen? Think about it. What will happen? Here, what will happen is that each thread has not only the single cell, but all the threads are even competing for writing into the single cell, right? So if I draw it more pictorially, what is now happening here is that there is one cell, and in this cell, multiple threads are trying to add value into it, right? So what each thread will do now is that it will compute its a of ik into a of kj. It will do this. Each thread will independently do this. And what it will try doing is that it will try the sum that, the product that it has computed inside this value, which is nothing but mult of ij. And when multiple threads try to write into this, so essentially it is not trying to write, but it is trying to read this mult, add this value, right? This value, this entire thing here, and again write back to the mult. And multiple threads are doing it simultaneously. So what will happen is that there will be a data race when you try to parallelize the third innermost, basically third loop. So now my question is again simple. How can we mitigate this? I think we have seen enough example. You should be now able to tell me how we can remove this thing. And I want multiple ways to do this, right? At least 2 or 3 ways. How can we remove this? We want to keep this thing. No? We just don't want to keep, we just don't want to remove this. So we don't want to remove this, but we want to ensure that the data race is removed. How can we do this?
So we can try to make this operation atomic. That's one way.
Okay, so what you are suggesting is OMP atomic, right? This is one way, definitely. This is the correct.
Mult can be shared. MELT, mult can
Mult
be
is already shared here. If you see, mult is already
Okay.
shared.
So another way is we could try using reduction clause for adding the elements to mult.
Yes, so this can be done, right? Reduction plus we have seen enough examples, right? So this should trigger your mind, right? When you see this, this mult is being, so this operation is being done for each thread. So this can be done in parallel, and adding to mult has to be done in atomic or in a more synchronized manner. So for this we can use reduction. So what you can do is you can do this. Right. So these are the 2 approaches, at least that I can think of. There can be others as well. Even you can place this in critical, but I think that won't be that efficient. But yeah, I think we can even place it in critical. That can also solve. But yeah, this is what we can do. And in general, if you want, if your matrices are not that large, then even you can skip parallelizing the innermost loop. But considering that you have parallelized it, what you can do is you can either use reduction or atomics or critical. So these are 2-3 solutions that you can have, right?
Can you tell me how this reduction works?
Yeah, so okay. Let me go back here. So if you recall from our sessions for reduction and synchronization and all those things, if you remember that the way the reduction works is that you have some operation being performed, right? So in our case, it was mult ij plus equals to a of ik into a of b of kj, right? So the way the reduction works here is that each thread will have the private copy for mult. So what will essentially happen in this case is that, let's say we have 4 threads. Then what will happen is that each thread will have its own copy. So T0 mult, T1 mult, T2 mult, and T3 mid, and they'll have the separate copy. And what they'll do is that they'll perform this calculation in parallel. So this calculation can be anything, right? Here we have just simple multiplication. This can be some complex function as well. Now each thread, what it will do is it will do this complex calculation in parallel, right? This is not causing the data race. This thing is not causing the data race. But what is causing data race here is this addition part. Addition, I mean reading and writing into this mult of ij. So what each thread will do is that it will do this thing in parallel and will write it into its separate copy. This write its answer in the separate copy, and this addition part, which is nothing but our reduction operator as well here, will be done in a synchronized manner. So that is how the reduction works.
Okay.
Okay, let me go back to the code screen. So essentially, they should be clear. If there are any questions, then please feel free to ask. Again, you can try multiple type of schedulings here, like static, dynamic, guided, and all those. Try playing with the size, and yeah, measure the time and see what, I mean, even play with the number of threads and so on, and try measuring the output time and see what difference you notice. So that is one. Now let us move to one more application. Maybe if we can finish this. Let us go to the slides. Right. So third one is stencil computation that we want to look into. So this is very similar to, okay, yeah, some kind of addition thing, but yeah, this is a slightly complex than addition. So you want to perform the stencil computation, right? Wherein each iteration, I mean, there are multiple iterations here, and within each iteration, what each cell does is this thing, this computation, which you can see. What it does is that it reads the value of aij, and then adds the value of ai minus 1j and ai minus 1j plus 1 into a of ij. I mean, adds this value into a of ij and write it to the a of ij. So that is what it does. So that is what each cell does. I mean, each entry in the matrix does. And again, the number of rows are from 0 to n minus 1. Number of columns are from 0 to m minus 1. Essentially, this is what we want to perform here. And the boundaries remain at the end of the computation remains intact. And we have initialized a to all ones in the our original matrix, and we are trying to run this thing for 10 iterations. So okay, let me show this thing more visually so that you can understand it quite better. Let me go back here. So now we want to do this stencil computation. So we have this matrix A. Okay, I think I quit. Yeah, so we have this matrix A, in which we told that we are initializing all the values to 1. Right? So all the values are 1. Right? Now what we want to do here is that we want to do this, right? A of ij is a of ij plus a of I minus 1j. I think it was I minus 1j plus 1, and a of I, let me check back. I think I might be wrong here, but yeah, this is correct. A of I minus 1 and j, right? So this is what we want to do essentially. So coming back to the whiteboard, yeah, so here, this is what we want to do, right? And what this translates to in terms of visually interpreting it. So what we are doing here is that let us pick up one particular cell. What we are doing is that we are adding these entry, and the center, right? So these two things, right? We are adding it inside this two, right? And yeah, so this is what we are doing in stencil computation in our example. So now, we are doing this for 10 iterations, right? So this entire thing will be done once, then again it will be done second time, third time, fourth time, 10 times, right? So that is what we mean by iteration count as 10. Now, please think about what will be the serial code for this, right? First of all, give me some vague idea about like vague or some high level code, how high level serial code that we will be using here. I'll wait here for a minute so that I can get some clue around what you people can understand by looking this thing. Or if you are not able to write the entire high level code or something like that, just give me just give me the idea about how many iterations will be there in the serial code, and at each iteration what we'll be doing. That is what I just wanted to know from you people. Right? So this is what we want to do. Any thoughts? Anyone?
So for serial code, if the matrix is of size m cross n, then number of iterations should be m minus 2 into n minus 2 for the serial code.
Okay. Got it. Yeah, I got it. But that is correct. But I think it should be m minus 1 rather than m minus 2.
Okay, yes, I misread the equation. Yes, it's m minus 1 into n minus 1.
Yes. Because we'll discard this thing, right? We'll pull this out. Since we are always reading, I mean, each time we need to read I minus 1, right? So we just need to leave this row. We need to start computation from here, right? From the second row. First row we need to discard, because for first row there is no previous row, right? So there will be no I minus 1 for that case. Now, coming back to this part, right? We are also reading j plus 1. So for last column, there won't be j plus 1. So again, we can't do this equation for the last column. So number of iterations will be m minus 1 into n minus 1, right? So that is correct. And one more thing that you should note here is that this is about the innermost two loops, right? So outermost loop, outermost for will run for 10 iterations, right? Because we want to do this computation for 10 times. Innermost, I mean, the second inner loop will go for 0 to m minus 2 because there are m minus 1 iterations. And the third one will go for 0 to n minus 2. So this is how it will look like. I hope this is clear. So let us look into the serial code quickly for this. If I have this, yeah, I have this. Okay, yeah, so I think this is the one, yeah, serial stencil.cpp. So this is how the serial code will look like, right? As we discussed. So we'll initialize it to all ones because this is what is given in the problem statement here. Then what we'll do is we'll run it for 10 iterations as we saw. And then I think we have kept m and n equal here. So we have n cross n matrix here and not m cross n. So this is fine. So what we are doing is that we are running from 1 to n, that is n minus 1 iteration. So first, as we discussed, right, that first row will be discarded because for that there won't be any I plus 1. So we'll start from second row, which is the which is I equals to 1. And again, we'll discard the last column. So we'll go from 0 to n minus 1 and not, 0 to n minus 2 because it's a less than symbol, right? Here, it's a less than 1. So less than n minus 1. So we'll go from 0 to n minus 2 and we'll discard the last column. And then inside we are doing this simple stencil computation, if you see, based on our formula, right? Stencil of ij is nothing but addition of this two thing, and we are adding this to stencil of ij. Cool. So this is clear, right? So far they're clear here. Now the question is simple again. Which all loops can we parallelize here? Forget about the initialization part because parallelizing the initialization part will be easy. We can parallelize both the loops as we saw for matrix multiplication, right? In that case also we were initializing the matrix to all zeros using these two for loops, right? In similar way, we can parallelize these two as well. So that is not the issue here. The issue is that how many of these loops can we parallelize here? That is the question. Can anyone quickly suggest me the number of loops here? There are 3 loops here, by the way. The number of loops that we can parallelize here.
So I don't think we would be able to parallelize any loop because there's a loop carry dependency for the stencil matrix.
Second
Okay.
loop, I think, can be parallelized. Second loop only.
Okay, someone
Sir,
suggested
just to
second.
confirm,
Yeah, please go ahead.
first loop is like that we have to perform the same action on the same set of data, right?
Yes.
Like it is
So
just like 10 times we are updating each number.
yeah, so this is the
So
important point. Yeah, this.
second
Please go
loop
ahead.
only.
Yeah.
Then I think second loop only.
Yeah, so what you suggested was important. So these can't be parallelized. First loop anyways can't be parallelized, right? Because this is the loop in which we are doing same operation 10 times. So we just can't parallelize that because this is inherently serial, right? Only after one iteration is finished, we have to start the second one. So this can't be anyways parallelized. Now the question comes that, okay, this we can't parallelize, but what about these two inner ones? Someone suggested that we can't parallelize any of them. Someone suggested that we can parallelize the first one, right? Any other suggestions apart from that? Anyone? Think about it. Like, think in the way we walked out through the previous two examples, right? So I took those two because that will help you to think about how we can parallelize these loops.
Sir, I think second one also cannot be parallelized because it is rows, right? It is setting rows. So if let's say third row comes first, then first row comes, then maybe the result will be wrong. So yeah,
Yeah.
even second cannot be parallelized.
Yeah. So okay, let us think about it. Think through this one. So the important point to note here is the way we are doing some operation, right? So let me go back to my whiteboard here, right? So do you see the way the computation is arranged, right? What we are doing here is that each entry, what it is doing, each entry, it is reading from the two entries that are there in its previous row, right? Those two entries are there in its those two are coming from its previous row. So just think about it. If if you're reading something from previous row, you can't assign multiple threads to different rows. I mean, each thread can't have different rows and work on the elements of each row. So doing this will be wrong, right? Assigning, let's say, let me erase this. Assigning row 1 to thread 1 or thread 0 and second row to thread 1. Now considering that there are also other rows that are above this one, what might end up happening is that okay, I think I have a visual representation for this. Let me share my slides. So this is the serial code and we've seen this, so nothing cool happening here. The important part is this, right? So let us say that you are doing this computation, right? So here what is happening is that some thread which is working on this row, which is our second row in this case, is reading the value from these two and writing it into this cell. Now, what is happening is that the thread that is working on third row, which is this one, is reading the value from these two and writing it into this one. So what might happening here is that there might be a data race because this thing is being read by a thread which is working on second row. Sorry, written by the thread that is working on second row and read by the thread which is working on third row. If we assign the threads with different column, different rows, so each thread is working on separate rows. If that happens, then there can be a data race. But think about it. Now, you can't assign different rows to different threads. That is fine. We understood there can be a data race here. So what can you do here? You can assign different columns to different threads, right? That can still happen. Now, think about it, why this can not lead to a data race? Because if I go back here, let us pick this one. So here what is happening is that, let us say that thread 1 is working on this column, some entry within this column here, right? And thread 2 is, okay, let me pick up this one. And thread 2 is working on, this is T1, this is T2, right? Now they are working on two different entries which are in two different columns. Now this thread is reading from here and here. Reading and writing from here and here. This thread is reading and writing from here and here. Can you see any data race here? No, right? At least to me, it is not evident that there is any data race here, because if two threads are working on separate columns and writing to two separate columns and reading from the previous row, then there is no data race, right? So the point here is that I'm trying to drive here, right? If we pick up this code, right, what you can do is that you can safely add hash pragma OMP parallel for here. According to me, there won't be a data race, but you can even think, at least I have checked that there is no data race if I do this thing. So this is fine. According to me, this is fine. Now, try to think one step deeper here. Like, let us say that if you want to even parallelize both the loops, then how can we do that? Please think about the way in which we can parallelize both the loops. And even, please think about it and please post your answers in chat, or maybe you can unmute yourself and tell me what your findings are. Okay, I'll maybe wait here for a few minutes to think, for you people to think about. Okay, any suggestions? Anyone? We have already seen how to tackle this issue, right? If you remember, there was one example where we used first private to remove the data arrays, right? So the idea there was the private copy for each thread, right? When you used first private for removing the data arrays, what essentially you were doing is that you are creating separate copy for separate copy of that variable for each thread. Try to apply the same thing here. So how can you do that? So the idea, if there are no suggestions, then maybe I'll add it quickly here. The idea here is simple. If we want to parallelize both the loops, what we can do here is that we can do this thing, right? Let me go back to a new page here. What you can do here is that you can use two copies, right? Previous stencil and stencil. And what you can do here is that this previous stencil will have the initial values, which are all ones, and it will keep on updating with each iteration. You can copy this computation back to previous stencil after each iteration. You can do that. But yeah, considering that these are the initial values, what you'll do is that you'll just keep this one for reading purpose. You are creating two separate copies now. You'll keep this part for just reading purpose, and you'll fill up each entry here by reading the values here. So now think about it. Even if you have each thread for separate entries, I mean separate cells here, there won't be any data arrays even then here, because you are just using these entries here for reading purpose. Right. So what I was telling is that we have separated the reading and writing part here. And by doing that, we are not reading as well as writing, or writing at the same time within the same variable using two different threads. So this is how we can even eliminate the data arrays for both the loops. And if we do this thing, right, if we implement this idea, what we can ensure is that we can parallelize both the loops. So that is what I was trying to highlight here. Any questions so far? Anyone who think that, I mean, anything that was unclear with this explanation? Anyone? Okay, if things are clear, then let me share my code screen again. Yeah. So there are two ways in which we can implement this stencil computation in parallel. One is this in-place computation, right? In place, we are not using separate uh, matrix, which is previous stencil, right? Which we used in our previous idea. But if we do that, then we can't parallelize all the loops. We can just parallelize the innermost loop, as we saw in this example. We can just parallelize the innermost loop. So for in-place stencil computation, we can just parallelize this one. For stencil computation, where we use two separate copies, which are respectively this previous stencil and stencil, we can parallelize both of this loop, right? So if you see here, I have parallelized both of these loops. And the way the computation is being done here is simple. So I've declared stencil and previous stencil, which are of size n cross n. I've done nested parallelism. I've done the initialization. Initialization does set the value for both of them to 1. I mean, each element within this stencil and previous stencil are set to 1. Then I call this function compute. In compute, what I do is simple. I keep this previous stencil for reading part, and this stencil as stencil for writing part. So the reading and writing are now separate. And the thing here to notice is that I think I should do this also, right? This should also be done. Otherwise, still it will be a data arrays. Yeah, I think this should be also done. Okay, so reading and writing are separated now. So we are just writing into stencil and reading from previous stencil, right? So this is how we can remove the data race and parallelize both the loops. I think parallelization is wrong here. It should be OMP here. OMP here. Yeah, anyways, but I think you are getting some idea from this thing, right? So this is how we are able to parallelize both the loops. And at the end, what we are doing is that we are copying this computation, which is there in stencil, into the previous stencil by again using this nested loops. And again, we can parallelize both of these loops because yeah, this is similar to initializing
I have a
particular.
doubt in this parallelization.
Yeah.
So won't this be giving a different result than the parallelization that we were doing before? Because in the previous one, we were using the updated call, like the row that we were utilizing in an iteration was updated in the previous iteration.
Yes.
But in this case, we are only reading the value from the matrix that was initialized. So that's all one, and it's not updated for every iteration.
It is being updated. So this is the point, right? For each iteration, which is ITR, I'm hoping that you are talking about this iteration, right?
No, so by iteration, I mean iteration of the column in a matrix. So it's not recalculation. So by iteration, I'm referring to the I loop.
For I loop, it is not being updated, is it? It is being updated, right? Okay, let me think about it.
So in the previous one, because we were not parallelizing the I loop, what was happening was when we started updating the value in the inner loop, it was utilizing the value of stencil I minus 1, right? That's what the row at which it was calculating. And then when in the next iteration, so the previous row would become I and the current row would be I plus 1. It would be reading values from stencil I, which would have been updated in the previous iteration, right?
Got it. Yeah.
But
So
in this case, that's not happening.
this is correct. Your observation is correct. So what will happen here is that I think what you suggested is correct. If I keep this, I think still there can be data race as such. Is it? Yeah, this might give incorrect result, right? Because what as suggested, what can happen here is that, let me go back to the whiteboard. What can happen here is that, yeah, so what can happen is that, no, I don't think that, okay, let me think a bit more. So can you visually tell me what you are thinking? Because I still think that both of the loops can be parallelized. And why are you suggesting that only one can be done? So are you trying to say that this one will be updated and we are reading the updated value and updating this one, is it?
Yes, sir. In the previous one, that's what was happening, not in the current.
Oh, okay. I think in that case, yeah, then you are correct. Let me check if that was the case for the previous one. Okay, for the serial one, okay, let me go to the serial part. Cancel this one out. Let me remove this for now. Let me see what's happening for serial one, right? For serial one, we are going through 10 iterations. Within that, we are going through this part and J1. Yes, yes, you're correct. So, yeah, assuming that, so we are taking the updated row, right? So, assuming that this is happening, okay. Yeah, if that is the case, then yeah, we can't do this. Okay, let me go back to the this one. Yeah, so you are correct. If you want to ensure the correctness here, then I think we need to remove this one. This one. But if we consider the case where we are not reading from the updated row, which is the case, okay, which is the case if we use some separate copy in which we are storing this stencil. during each iteration, right? So as I told, right, one iteration is being used for reading, and one copy is being used for just reading, and another is being used for writing. In that case, we might be able to parallelize both the loops. But yeah, you are absolutely correct here that for this case, considering this is the serial program for which we are trying to write the parallel version, this might be the incorrect one if I remove this. If I uncomment this one. So yeah, so this is the correct observation. Any questions up till now? Anyone? So I need to comment this part. Okay. So based on the problem statement we saw, then I think we can just parallelize the innermost loop and not the outer loop. Any questions?
Sir, but even in this implementation, the previous stencil matrix is not being updated, so the result would be the same as we were getting before.
Why we are updating it right here? Is it that it will not get updated?
Okay, so we are updating it after each iteration. Okay, got it.
Yes. Yes. So we are writing it in stencil, and after that fresh computation has happened, we are reading it back here, right? So that is what is happening. After fresh computation, we are reading it back in the previous stencil. And during next iteration, we are using that previous stencil. So I think this is correct. We can at least parallelize the inner one. But,
no, sir, but I think it will still give us wrong result. Reason being, so we only need the updated row at a time for next I value. So if I is equal to 1 is running, in I is equal to 2, we need the updated value which was there in I is equal to 1.
Yes, so that is correct. Updated row will be there, right? Because we are executing row serially. So that is
yes,
what
but
is in this point. Yeah.
But when, so for example, when we come from I is equal to 1 to I is equal to 2, we will be updating this third row of stencil by referring to the previous stencil's third row as well, right? But sorry, we will be referring to the previous stencil's second row, but the second row would still not be updated according to the previous iteration.
Got it. So the point that you are trying to say is correct. Let us go back to this as well. So these are good points. I think every one of us should get this one right when we are trying to parallelize this one. And these are the important observations as well. So actually, I'm expecting from each and every one of you to give this, try to get these points out when I'm trying to explain, because there might be something wrong that I might be saying, and you should be able to figure this out. So let us see what the suggestion was here. So let me go back to the whiteboard here. So what was being suggested here is that this can still give a wrong output. Why? So what might end up happening is that if I understood it correctly, then what might end up happening here is that during computation, what we are doing here, right? If we execute it serially here, let me go back to the code screen. Do I have the serial part? Cancel it. Okay, yeah. So during serial execution, right? During each iteration, what we were doing, we were reading this stencil of ij, and that was happening serially, right? So let me go back to my code screen. So let us say that you are trying to update this entry here, and what will happen is that this initially all the values were 1, right? So this this value as well as this and this one will be read here and will be updated here by adding this from the previous stencil, which is this one. Now, in case we have parallelized the inner loop, what end up might happening here is that this one might have the stale value. Is that what you are trying to suggest?
Can you repeat that one?
So you are trying to suggest that this value can be stale, is it?
Yes, so that would do this value would be updated based on the old values, that so the row wouldn't be updated.
But okay, correct me if I'm wrong here, but these three values are being read here, right? And those can those be old? Which is fine, right? This should be always be one, right? This value should be one always. Can this be something else?
So in the first iteration, that would be true, but suppose we're going to the next row, for example. So in that
Okay.
case, now that value would be 2, right?
Yes. So yeah,
So
that
it
is
would
correct
be 2,
observation.
1, and the value in below 2 would be 1. So it should be 3 in the next iteration. But if we use the previous stencil matrix, it would still be 2.
Yeah, but that can be eliminated, right? So yeah, your observation is correct here, but let me update update code a bit. Can we do this then? Okay, let me go back here, right? Can we do this then? Will this correct it? Now it will take the updated value, right? In this case, it will be fine, right?
It has to take the updated value of the
Yeah.
previous row, right? So that should be a stencil of I minus 1. So that would anyways make it to like the previous code that we had.
Okay. So okay, let me go back to the whiteboard here. So you're trying to suggest that okay. So you're trying to suggest that if I'm not wrong, but let me correct. I mean, please correct me if I'm wrong. But this one, uh, these two values are okay. First, let us consider that we are trying to update this value using our formula, right? So this is the value which is currently under our uh, uh, currently we are trying to update. Now, assuming that we are reading it from stencil here, so we'll be reading the value this one, and we'll be updating these two, right? Sorry, we'll be updating this one, and we'll be reading these two as well as this one. So, can there be an issue here? Is the question. So, okay. I think this should work, right? Why do you think that? Oh, okay, got your point. So you're trying to say that these two can be stayed here, right? Which will be updated in this case. So is it what
Yes,
you are trying to suggest?
yes, sir. So the previous row in the previous stencil matrix would be stale
So
because they
these two can be, yeah. So the point is correct. These two can be stale, and we are trying to read these two and update these one, right? So that is the point. Is it correct?
yes,
Is
sir.
what you're trying to say? Yeah. So what can be the possible mitigation for this? Is what I'm trying to think here.
So I don't think we would be able to mitigate this if we want to parallelize the loop. We would have to use the previous implementation, which was just using one stencil matrix.
Okay, maybe I can suggest something here if I'm thinking it correctly. But yeah, please correct me if I'm wrong here. What we can do is that after each row computation, right? As we saw for first row will be correct. So after each row computation, we can copy the values in the previous stencil. Will this solve the problem?
Yes, sir, that could work.
So essentially the solution to this problem could be, yeah, so this code is incorrect, which is the correct observation. This code is incorrect, right? But the simple solution is that instead of doing copying here, we are copying right here, we can do within the outermost loop. So here there should be a copying logic, right? And doing this will solve the issue, and we can at least parallelize the inner loop. And yeah, still we can't parallelize the outer one because of the stale value issue. Even if we have removed the data race, there can be the stale value issue, which can happen. So I hope this is clear. Any questions on this? Any further questions or anything that you feel that was wrong in this code? Then also please feel free to add. Yeah, by the way, thanks for the suggestions so that, I mean, yeah, we all learn by this thing, right? So please feel free to add suggestions. Okay, let me, if there are no suggestions, then I think we have already overstretched the time, so maybe I'll stop here. I think that was all even I wanted to cover for the today's session. So the in-place stencil computation and the stencil computation where we can use the uh, separate matrix here. So that was the second one. So that is what I wanted to cover, stencil computation with extra space. Okay, so far I think then we are done with all our sessions for this OpenMP programming part, and I won't take much of your time here, but if there are any questions here, then please feel free to ask. And yeah, to summarize, like we saw the applications in this session, and we tried to pull together all the things that we have learned so far in terms of adding those things to the applications. And yeah, on next Saturday, we'll have a test, which will be 1 hour test. And yeah, the questions will be simple, mostly straightforward. So if you paid attention to the sessions, then we will be mostly able to solve them. And yeah, I'll wait for the questions. And thanks everyone for being with me for all these 9 sessions. And it was even wonderful journey for me to learn from all of you. So thank you. And yeah, I'll wait here for a few more minutes to take up the question. And yeah.
So, according to the itinerary, I think there's one test remaining, right? So, how would you be conducting that?
So the test will be on next Saturday on 5 p.m. if I'm not wrong. So for the test, I'll be sharing the Google form with you for all of you, and you'll be answering the questions within the Google form. It will be an MCQ based exam, and it will be 1 hour exam. And yeah, after the exam and after filling the feedback form, there will also be a feedback form. We can conclude this course.
Okay, sir.
Okay, any questions, any suggestions? How do you feel like after going through all these 9 sessions? Like, do you feel a bit more confident with OpenMP, or do you feel like something was missing or anything should be added? Please feel free to let me know either via group, or you can even paste it here in chat, or you can unmute and ask and tell your suggestions. Either way is fine. Okay, I think there are no questions. Then we can call this a meeting, and see you all on next Saturday at 5 p.m. It was a great learning experience from all of you. Thank you for joining and being part of this course. See you all on Saturday, and I hope all of you will be able to score good marks in the test. Thanks. Thank you. Bye.